Welcome to the last talk of session 2 of ViViMaT. Our final speaker, Brandon McClimon, took a bit of an unusual path to his current research career. He first earned an engineering physics degree at the University of Michigan, but then became a junior officer in the US Navy. He completed a 5-year tour on a nuclear submarine, then worked as a nuclear engineer at the DC Cook power plant in Michigan for several years before getting his master's degree at the University of Virginia. He recently finished his PhD at the University of Pennsylvania, studying DLCs in the group of Rob Karpik, primarily using atomic force microscopy. I'm looking forward to his take on the hunt for Red October. Don't forget to post your questions below, and Brandon will be with us in a jiffy. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, amorphous carbon.
Hello everyone, thank you for watching my talk today. I'll be talking about a diamond-like carbon material that's referred to as silicon oxide-containing hydrogenated amorphous carbon. And we'll be looking at the tribological response to learn a little bit about the friction mechanisms. And we're going to do experiments on multiple length scales in hopes that we can extract some useful insights about what controls the friction that we see at larger length scales. And so I should start by talking about the particular material here, which is a subset, a larger class of materials referred to as diamond-like carbons. And these particular materials are very attractive in the tribological world because they combine two unusual properties, low wear and low friction at the same time. And so ideally we want a lot of materials like this, and so it's useful to try to understand what gives these very attractive properties. And so one way that's been understood for a long time is that the response is controlled by two important parameters of the film structure. This ternary phase diagram tends to summarize this, and we have hydrogen on the x-axis down here. And films that are very high in hydrogen have low friction in inert environments, and if they have low hydrogen, you tend to need a reactive environment, typically water vapor, to have low friction. Additionally, on the left axis here, we have the carbon hybridization ratio, and this can range in these materials from almost fully sp2, so it's a soft graphitic type material, all the way up to very highly sp3, where it's very diamond-like. And this basically controls the wear rate in these systems. And so the particular material I'll be talking about occupies the center of this diagram, and it's a variant of hydrogenated tetrahedral amorphous carbons, or right around here. And these materials in general are becoming more and more industrially important all the time as the price of depositing them gets cheaper and cheaper. And so you're starting to see them in things like mid-priced cars as low friction components like piston liners. For a long time, you've seen them on machine tools. DLCs excel at machining, for instance, aluminum. And then these carbon-based materials are very biocompatible in general. And so you see them in a lot of medical implants, such as this knee implant here. Researchers have wanted to improve the properties of these materials for a long time, and one way to change the response of them is to dope them with various elements. And so the particular material I'll be talking about today is doped with silicon oxide. And this is known empirically, and now the reasons why. It's known that they improve the thermal oxidative stability of DLCs. And so this makes them attractive for applications like, for instance, solid lubricants in low Earth orbit, where you have a lot of charged particles flying around that tend to erode undoped diamond-like carbons. And then also the hard drive industry is trying to go to a higher density recording technology by using very high temperatures in the storage media. And these storage media have always been protected by hydrogenated amorphous carbon, and it turns out these high temperatures lead to very rapid oxidation. And so by doping the materials with silicon oxide, you can actually reduce that quite a bit and make them a candidate material for this technology. So I'll talk a little bit about the theories of lubrication of these materials. The first one is very dominant in the literature and is referred to as surface passivation. The way this works is that high friction in these materials is known in some cases to occur because of interfacial bonding across the interface. So chemical bonds form between the diamond-like carbon and whatever the counterface is. And if you can prevent the formation of these bonds, you can reduce the friction. This is done by, in some cases, doping with hydrogen. So some of this hydrogen can end up on the surface, and so you'll have a hydrogenated surface that doesn't tend to form bonds. If it's not doped with hydrogen, you can actually get passivation from the environment. In this example, water molecules can actually land on the surface, dissociate, and then terminate dangling bonds with either hydroxyl groups or hydrogen atoms, which in both cases tend not to form additional bonds across the interface. The evidence for this mechanism being important is really overwhelming. There's a lot of it, both experimental and simulation, showing that this is a necessary condition for low friction in these systems. The other one is the formation of a transfer film, which we refer to as a tribofilm. And so basically how this happens is some of the diamond-like carbon actually gets transferred to the counterface. So then you have this film sliding against the diamond-like carbon. And it's been known empirically for probably 30 years that this is really important in achieving low friction. If you don't have the tribofilm in a lot of DLC systems, you won't have low friction. And so researchers have tried to figure out how they work for a long time. A lot of the early research suggested they might be graphitic in nature. So the low friction mechanism is just graphite sheet sliding against a graphite sheet. But newer spectroscopic work suggests that these films might be polymeric based on the fact that they're heavily enriched in hydrogen and their density is quite low. So in fact, these might be polymeric in nature. The example I show on the right is actually a tribofilm from my Macroscale sliding experiments. My way of trying to understand the response of these materials is a multiscale one, looking at different length scale contact diameters. So at the smallest length scale with contact diameters below 10 nanometers is what we refer to as nanotribology, where we take a very sharp AFM probe with a radius at the tip that we can characterize quite well and slide that against the material of interest. And this is really useful because the fact that we have a well-characterized single asperity means we can apply standard contact mechanics to understand what's going on. So we can learn things like what the real area of contact at a particular load is. The second length scale with contact diameters below a micron is what's referred to as the microscale. And so in this case, the experiments I did, we glued a steel colloidal ball on the end of an AFM cantilever and then did sliding experiments in the AFM again. And this is useful because we can measure the various parameters that we can get from the atomic force microscope, like adhesion and topography. But additionally, in this particular material system, we actually see effects which don't occur at the nanoscale. And so that's going to be important for what we talk about later. And finally, we look at the macroscale. So we do experiments to measure the friction response when you have nominal contact diameters above 10 microns or so. And this is important because this is the tribological response that's relevant to industrial application. You can extract things like the friction coefficient and the wear coefficient that will be useful to anybody trying to apply these materials in the industrial world. But additionally, if you gain insights about what's happening at the smaller length scales to apply them at the larger length scales, you have to know empirically what the response actually is at the larger length scales. So I'll start here with the macroscale response, which was obtained by using a ball and flat tribometer, like you see here on the top right, in a controlled sliding atmosphere. And so an example curve that we got here is what you see in the graph. On the y-axis, we have the friction coefficient. On the x-axis, we have the sliding cycle number. And the response that we see here is very prototypical for hydrogenated amorphous carbons. It starts out with an elevated friction coefficient, and then over some small number of sliding cycles, we'll have a reduction in that friction coefficient, and that's what's referred to universally in the literature as the run-in effect. And then after that's complete, it settles in at a relatively constant steady state for thousands of sliding cycles. And the absolute value of the friction coefficient is very low, below 0.1. And this is typical for hydrogenated amorphous carbons sliding in inert environments. And in this case, the sliding environment was dry nitrogen. So that's the response at macroscale. Moving down to our smallest length scale now, I'll talk about nanoscale experiments. And these were done with a sharp AFM probe sliding in contact mode on the sample surface. And ideally, the tip is shaped like a single asperity, so with a tip radius below 30 nanometers or so. And I actually made two sorts of measurements that I'll show momentarily. And the first one is what I'll refer to as standard imaging. So every scan line, the tip moves such that it's sliding on fresh material. So any friction response that we see here is the inherent friction response for the unworn material. And then the other way of making these measurements is what's referred to as reciprocating sliding. So we just slide back and forth just like a tribometer does. And so there will be some evolution in the friction response that's due to transformation or wear of the underlying sample. And so comparing these two can be useful, as I'll show in this slide. On this slide, we have a nanoscale friction result. And so this was done with an AFM probe that was coated with tetrahedral amorphous carbon. So that's just another diamond-like carbon that's very highly sp3 and low in hydrogen. And this is useful because it has a similar magnitude of hardness to diamond. And what that means is that it's very stable against geometry changes. The way this experiment was run was we started at a very high normal force of 200 nanonewtons. And then we progressively reduce the load every scan line until the tip eventually pulls off the surface. And what you can see in the imaging case, where every scan line is on fresh material, is that there's a linear scaling between across the load range. And that linear scaling is indicative that we actually have a multi-asperity contact. And the slope of this line can be compared to a friction coefficient that you would get based on Amonton's law. If we switch to looking at the reciprocating sliding result, we see very different behaviors. The initial friction starts at a similar value, but then it drops rapidly. And so this rapid drop in the friction, we think, is akin to what is happening in the macroscale run-in process. There's some initial transformation of the sample surface that causes the friction to settle into a lower value. So we think we're capturing some of what happens with the run-in process. Additionally, since we know by repeating these trials multiple times with the same result that the tip geometry is not changing, what that means is that at a given load, there's the same real area of contact between the imaging case and the reciprocating case. And given that the friction is at a lower value, that means there's some change in the interfacial shear strength that's happening as a result of this run-in process. And so it seems like the parameter to be interested in here is the interfacial shear strength. And so given that, we want to actually know what the interfacial shear strength is. An advantage of the nanoscale measurements is that we can actually measure that and calculate it. And the way we do this is by doing something called a lateral stiffness measurement, where we oscillate the tip laterally and measure the force response. And from that force response, we can actually calculate what the real area of contact is. And since we know the friction response and the real area of contact at a given load, we can calculate the shear strength at any given load. And so what's done here on the right, in the case of two different probe materials. So in the top case, we have a hard diamond probe, and in the bottom case, we have a tetrahedral amorphous carbon probe. And in both cases, the response is quite similar. So what we see is when we compare the imaging mode, we have a much higher shear strength than we do in the reciprocating mode. So that's indicating that this run-in process drives down the shear strength as we expected based on the results of the last slide. And so this run-in process gives you a lower interfacial shear strength. Additionally, what we see is that the shear strength is approximately constant across the entire normal force range. And that's true with both probe materials and both imaging techniques. And that'll become relevant later on in the talk, so I'll talk a little bit more about that. But the final thing to note is the actual absolute value of these shear strengths. They're astronomical. They're in the gigapascal range. And just as a frame of reference, the hardness of the silicon-doped DLC is around 10 gigapascals. So the interfacial shear strength is of the same order of magnitude as the hardness of the starting material. And that sounds like it's high friction, and it is high friction. And another way to quantify that is that macroscale sliding experiments, certain ones can actually provide estimates of what the shear strength is in macroscale sliding with diamond-like carbons, including silicon oxide-doped diamond-like carbons like the material I'm studying here. And whenever that has been done, universally they find shear strengths below 100 megapascals. So that's orders of magnitude below what we see, and intuitively that's what you would expect, given that we know that diamond-like carbon materials are good low-friction materials in macroscale sliding. So there's a disconnect here. Something very different is happening in these nanoscale experiments than what ends up happening in the macroscale experiments. And so one hypothesis you might have about what's driving the difference is the tribofilm, given that in these nanoscale experiments, we typically did not see any evidence of tribofilm growth. And so we really are interested in what the effect of the tribofilm may be, given that we don't see lubricity really in the absence of the tribofilm. To get at that, we switched to a different length scale. So we moved to the microscale now, where we can have a multi-asperity contact, where maybe different phenomena will occur. To do this, we used a steel colloid and we glued it onto the end of an AFM cantilever and then did more experiments in the AFM. In this case, we do reciprocating sliding akin to what is done in a tribometer. So this gives us the advantage of being able to monitor multiple signal channels. So we have obviously the friction force, but we also were able to monitor the topography. And finally, we also imposed a normal oscillation on the tip. And then by measuring that force response, we can calculate what the normal stiffness of the contact is, which is useful for seeing any changes that might be occurring due to perhaps the formation of a tribofilm, given that we expect the tribofilm to have a much lower modulus than the starting material. And so here's an example of one of these experiments. So if you look at this graph on the left, we have multiple signal channels, like I mentioned. We have the friction force, the normal contact stiffness, and the probe height. At the start of the experiment, we have a friction force of about 8 micronewtons. And then over about 200 or 300 sliding cycles, you can see that this rises about 50% up to about 13 micronewtons. And we attribute this to the fact that this steel ball is bumpy and will have a bunch of asperities in contact. And there will be wear of these asperities, which will bring more asperities into contact and therefore increase the real area of contact between the ball and the sliding surface. And that will naturally lead to higher friction. But then there's a very, very dramatic thing that happens at about 300 cycles. There's a very dramatic drop in the friction force. And the drop in this friction force we attribute to the formation of a tribofilm based on 3 lines of evidence. The first one is that the normal contact stiffness changes dramatically at exactly the same time. And it actually goes up, not down. The fact that it goes up tells us that there's in fact a big increase in the real area of contact, because we know from other experiments that the tribofilm that forms is going to have a lower modulus than the starting material. So that would tend to drive down the contact stiffness, but in fact it goes up, indicating that the real area of contact is going up quite a bit. Additionally, the probe height goes up. And the reason this happens is because we are in load control. So if something grows in between the 2 sliding surfaces, the tip has to move up to maintain the same normal load. And so that's what we see here. And then finally, we have imaging before and after the image, where we reverse imaged the ball surface. And what you can see is that before the experiment, the ball is very, very smooth, and we only see the hemispherical shape. And then after the experiment, we see, in fact, that the tribofilm is formed here. And the thickness of this tribofilm matches approximately the change in probe height we measured throughout the experiment. So I think this shows pretty conclusively that we form a tribofilm and that the tribofilm is responsible for a huge drop in the friction. We can learn one additional thing by zooming in on the area where the friction drop occurs. So this is from cycle 2 to 300 or so. And what we can see is when the friction drops about 80% from its maximum value, the change in the probe height is only about 2 nanometers. So what this is telling us is that while the tribofilm provides a lot of lubricity in the system, this lubricity is a near surface effect of the tribofilm. So the fact that the tribofilm grows to 30 nanometers, the bulk of that tribofilm is not participating in lubricating the surface. It's only the top 2 nanometers or so that provides the vast majority of the lubrication. And so for future studies to try to understand where this is coming from, you only need a thin layer of tribofilm to drive most of the lubricity. We can do an additional set of analysis here. Now that we have a colloid with a tribofilm on top, we can actually measure the friction response of the colloid plus tribofilm case. And so to show this, we have our friction force versus normal force here, and we actually measured the friction force versus normal force in the bare colloid case. And as you might expect for this multi-asperity contact, we have a linear relation between friction force and normal force. But then if we switch to the case where there's a tribofilm on the colloid, what we actually see is that there are a number of changes that occur. The first one is that there's a huge drop in the adhesion, about an 80% drop, and it's all the more dramatic considering the fact that we know that the real area of contact between the 2 interfaces increases tremendously. But the fact that the adhesion drops means that if you shift this curve to the right, you'll have lower friction at any given normal loads. This is responsible for at least a part of the friction reduction that we see. Additionally, we can see that the shape of the curve changes a lot. So instead of being linear, it obeys a power law. And the exponent of this power law is about 0.52. And if this were a true Hertzian contact, you would expect a power law exponent of 0.66. In fact, it's a little bit lower than that. And we attribute that to the fact that the surface of the tribofilm is relatively flat, not hemispherical. So it behaves a little bit like a punch probe, where you would expect the power law exponent to be 0 instead of 0.66. So the fact that it's intermediate between these two makes sense. Additionally, the fact that this is behaving like a single asperity contact means the real area of contact is approximately equal to the nominal area of contact. And that's useful to us in that there's one additional piece of analysis we can do, where we make use of this Robbins group paper from Johns Hopkins from 2016, where they did a theoretical analysis of a multi-asperity hemispherical contact. And they show that at some critical load, the linear scaling between the contact area and the normal load shifts over to Hertzian scaling, because all of these asperities are compressed to the point where the real area of contact becomes equivalent to the Hertzian case. And so by extrapolating these curves to this critical load, and we could calculate this critical load because this paper gives roughness parameters to do so, and we know the roughness parameters from measuring the bare colloid case, we could show that this critical load was about 20 micronewtons. And so we know at 20 micronewtons, these extrapolated curves will have the same real area of contact approximately. And so what that means is that this change in friction force between the two is actually equivalent to a change in the interfacial shear strength. What this means is that this tribofilm is providing an interfacial shear strength reduction of about 80%. So I've already showed that adhesion and shear strength change a lot, and that's how the tribofilm provides low friction. But we're also interested in why does the tribofilm provide low friction? And we don't have a bulletproof answer for this, but we do have a hypothesis that's consistent with our data. Our hypothesis is that in the nanoscale sliding case, the high friction that we see is dominated by atomic and nanoasperity pinning and not interfacial bonding. And therefore, when we grow the tribofilm, we actually make one side of the interface very soft, and so that allows for easy depinning of the surface. And so that's how our friction is dropping. So why do we think this? Well, let's return to our nanoscale experiments for a moment. And I'll show here again shear strength on the y-axis, and then the x-axis has actually been converted to normal pressure. Over this normal pressure range, the dependence of shear strength on normal pressure is approximately constant. If there's any change at all, it might be a negative slope here. And how does that compare to a case where we have interfacial bonding across the interface? We know what that looks like based on a number of simulation papers, and I give one example here. So interfacial bonding is an Arrhenius type reaction, and actually we expect it to be stress assisted. So this gives you a simplification of the Bell equation here, where the activation energy to form an interfacial bond can be modified by an increase in stress, in this case, the normal contact pressure. And that reduces the activation energy, and therefore at higher contact pressures, you'll have more interfacial bonds per unit area, and therefore an increase in the shear strength. And so that's what they actually see here. They prepared this system such that it was deficient in surface passivation by only passivating 80% of the surface bonds. And in that case, they have a very positive slope of shear strength versus contact pressures. But as they increase the passivation by increasing the hydrogen at the interface, what they see is that the slope goes down and becomes more flat. So let's compare this to an example where there's no interfacial bonding. And again, we'll rely on simulations from the Robbins group. And this is a molecular dynamics simulation where the bonding potential was such that no interfacial bonds could form across the surface. And therefore, any contribution to the shear strength is just atomic pinning between atoms on each side of the interface. And in that case of an atomic pinning dominated system, what they see is that the shear strength is approximately constant with the contact pressure. And this is very similar to what we see in our nanoscale experiments. So this is why we hypothesize that what's actually happening in our system is friction that's dominated by pinning of some sort. So just to conclude here, the friction reduction that we see at nanoscale is at least partially due to some modification in the surface of the silicon oxide doped hydrogenated amorphous carbon. And we think this is at least part of what happens during the run-in process in macroscale sliding experiments. And additionally, we see in the nanoscale experiments that the absolute shear strength remains very high. So this is, despite the fact that this is presumably a well surface passivated surface, we see high shear strengths nonetheless. But in the case of a microscale experiment, what we see is that low friction in this silicon doped DLC is achieved immediately upon the growth of a tribofilm. And this friction reduction is due both to a very large reduction in the adhesion and a very large reduction in the shear strength. And this overwhelms a very large increase in the real contact area, which otherwise would tend to increase the friction. And so that's what's allowing the tribofilm to provide lubricity to the system. So I just want to acknowledge my funding sources here, and thank you for watching, and I'll answer any questions you might have in the comment section.